Hi everyone! Today in this lecture, I want to talk about the design of band reject filter by using active components. Similar to what we had for band pass filter, we need to use a low pass and a high pass filter. We need to connect them in order to have a band reject filter. But the configuration and the way that the frequencies are located are going to be different. So I need to have a low pass filter and a high pass filter. If you remember from previous lecture, for band pass filter, we needed to make sure that the cutoff frequency of our low pass filter is greater than our high pass filter cutoff frequency. But this time, for band reject filter, we need to make sure that the low pass filter cutoff frequency is smaller than high pass filter cutoff frequency. So it means that we are looking for something like this. So if I have the cutoff frequency of my low pass filter somewhere here, then the cutoff frequency of my high pass filter needs to be greater than this. So let's say somewhere around here. Let's call the cutoff frequency of the low pass as X and the cutoff frequency of high pass as Y. So I can describe the same constraint here in terms of X and Y. So Y should be greater than X in order to be able to design a band reject filter. So that's the very first constraint that we need to have. Now, the next question is that how should be the configuration? Should I cascade them? The answer is no. Why? Because if I cascade these to filter, what will happen is that the first filter will cut a portion of our frequency spectrum. So if, let's say, my low pass filter is the first filter in the cascaded combination, so it will cut all the frequencies greater than X. So the only frequency spectrum that reaches to this point are the frequencies smaller than X. So this is going to be the frequencies that can pass the first filter, which is my low pass filter. And then the high pass filter will let the frequencies greater than Y to pass the filter. Now, because only the frequencies smaller than X were able to survive the first filter, I don't have any frequency greater than Y. So the filter, the second filter, will cut all of them and no frequency can survive till my output. So all frequency will be cut either by the low pass or the high pass filter. So no frequency can pass the cascaded combination of a low pass and high pass filter, where the cutoff frequency of my high pass filter is greater than the cutoff frequency of the low pass filter. So now the question is that how should I put them together? How should I connect them? The answer is that I have to put them in parallel. So the solution is a parallel connection. By connecting them in parallel, what will happen is that frequencies can pass the filters either through the high pass filter or low pass filter. So if they can survive any of them, they can get to the output. So let's say this is my low pass, and here I have my high pass filter. Then I have to feed my input signal, which is Vi, to both of them. And then at the end, I have to add those signals together. So at the end, what I need to use is a summing amplifier. And then here I'm going to have my VO. So if I connect them in this form, what will happen is that the signal will go through both of them, and the filter will the low pass filter will cut this portion of frequency, and the high pass filter will cut this frequency spectrum. So from low pass filter, I'm going to have this part of frequency spectrum, and from high pass filter, I'm going to have this one. So my band reject filter is able to pass frequencies smaller than X, and that's possible through the low pass filter, and frequencies greater than Y by going through the high pass filter. So at the end, what I have here at my output is going to be a band reject filter, which has cutoff frequencies close to X and Y if X is much smaller than Y. So this is the constraint in order to have cutoff frequencies of my band reject filter to be similar to the individual low pass and high pass filter cutoff frequency. Remember that if my cutoff frequencies are not widely separated, still the response of this connection is going to be a band reject filter. So as long as I'm using two filters, a low pass and a high pass, in which X is smaller than Y, and X is the cutoff frequency of low pass and Y is the cutoff frequency of high pass. As long as the cutoff frequency of my high pass is greater than my low pass filter, I'm ended up having a band reject filter. So the result is going to be a band reject filter. Now, if I add another constraint, the second constraint is that not only Y is greater than X, but it is also much greater that I can assume that they are widely separated. In that scenario, not only I have a band reject filter, but also I can assume that the cutoff frequency of this band reject filter is exactly the same as the cutoff frequencies of low pass and high pass filter. Now let's look at the circuit, how the circuit of this band reject filter looks like. So what I'm going to do is that I'm going to draw the low pass and high pass filters separately, and then I'm going to connect them in parallel. So I'm going to start with the low pass filter on top. Okay, so here you can see the low pass filter on top, the high pass filter on the bottom of the page, and then I'm trying to show you the summing amplifier on the right hand side. So based on the configuration that I have here, I need to apply the input signal to both low pass and high pass filter. So here I'm assuming that this is my VI, and VI needs to be connected to both my low pass and high pass filter. And then these needs to be added together by a summing amplifier. How does the configuration of a summing amplifier looks like? The summing amplifier has two input resistors connected to the inverting terminal of the summing amplifier, and then each output of my low pass filter and high pass filter needs to be connected to one of these input resistor, which I'm showing them by RI. So the output of low pass should be connected to one of them, and the output of the high pass should be connected to the other one. And then here at the end, I'm gonna have my output voltage, which is VO. Okay, now when I'm talking about designing a band reject filter, the first thing is that I know that this is how the configuration of my circuit is. So I need to put these two in parallel and then use a summing amplifier and connect my output of low pass and high pass filter to the summing amplifier through an input resistor. And the design part and the main part of this design is coming up with appropriate values for my resistors and capacitors in order to have whatever gain or cutoff frequency that I need. So I'm going to show the resistance. So I'm going to show the resistor of my low pass filter by RL and the capacitor by CL. And for high pass filter, I'm going to consider them as RH and CH. Now remember that I'm choosing both resistor for low pass filter as RL, and for high pass filter both of them are RH. The reason is that I want to make sure that the gain of this low pass filter is equal to 1. Same thing here. So I want to make sure that the gain of my high pass filter is equal to 1. And finally, the last parameter that I need to take care of is the RF, or feedback resistor, of my summing amplifier. And this RF and also the value that I choose for input resistor, which is RI, defines the gain of this band reject filter. So at the end, in order to have a desired gain for this particular filter, I need to make sure that the ratio of RF over RI is equal to the gain that I'm looking for.